In this video, we're going to explore nucleophilic substitution reactions. The images and the examples are adapted from our Cognitive Higher Level textbook. So, halogenoalkanes undergo nucleophilic substitution, and the carbon that the halogen is attached to is considered to be electron deficient due to the difference in electronegativity. So that makes it easy for a nucleophile, so those are groups with lone pair of electrons or negative charges, to come in and displace the halogen from the molecule. Some common nucleophiles are hydroxide, water, ammonia, amines, and cyanide ions. So there are two different types of nucleophilic substitution reactions, SN2 and SN1. We'll look at the SN2 reactions first. So SN2 reactions are what happen with primary halogenoalkane. So remember, a primary halogenoalkane means that the halogen is attached to a carbon that has two other hydrogens. So it's said to undergo bimolecular nucleophilic substitution. So that's where the 2 comes from the bimolecular. And then the S is for substitution and the N is for nucleophile. So bimolecular comes from the molecularity of the rate determining step. And what that means is in this rate determining step in the transition state, we form actually a unstable transition state where the nucleophile is partially bonded, but the halogen hasn't quite left yet. So this first part is slow, and then there's a fast reaction after that. So in this one-step reaction, the nucleophile makes a backside attack. So you can see it attacking back here, and it displaces the halogen. So you can see the nucleophile entering in on the molecule, creating a carbocation, and then the chloride in this example is leaving. And that backside attack actually inverts the spatial arrangement of the atoms around the carbon. So now the nucleophile is entering from the back, and then the chlorine is leaving from the front. So if we were looking at the kinetics of SN2 reactions, because the rate determining step is bimolecular, the rate of the reaction depends on both the concentration of the nucleophile and the halogenoalkane. So the rate is equal to the rate constant times the concentration of the halogenoalkane times the concentration of the nucleophile, and in this case the nucleophile was hydroxide. If we were to look at an energy diagram of this, so we can see here our reactants. There's some activation energy to overcome. In this transition state, you can see that bonds are being broken while bonds are also being made between the carbon and the nucleophile. And then the products have a much lower energy than the reactants. So in SN1 reactions, these are when you have tertiary halogenoalkanes, and they undergo unimolecular nucleophilic substitution, so SN1, and it is a 2-step reaction. So in the first step, we're breaking the carbon-halogen bond, with the halogen taking both of the electrons with it. So we end up with a halogen ion. So this is a slow step. And then the second step is the nucleophile uses a lone pair of electrons, because remember, nucleophiles have extra electrons, to bond with the carbocation. And that step is fast. So there's the slow breaking of the carbon-halogen bond step, and then the fast nucleophile bonding step. So if we were looking at the kinetics of these types of reactions, because the reaction is unimolecular, the rate of the reaction is determined by the concentration of the halogenoalkane only. So in this example, the rate is equal to the rate constant times the concentration of the halogenoalkane. So because this is a two-step reaction, there are two transition states. So the first transition state is the breaking of the bonds, and the second transition state is when we're forming the new bond. The first reaction has a higher activation energy, so it's considered the rate determining step. So now we'll talk a little bit about carbocation stability. So the more alkyl groups that are attached to the carbocation, the more stability it has, because this causes steric hindrance, preventing backside attacks, which will lead to SN1 rather than SN2 substitutions. So a primary carbocation is less stable than a secondary, which is less stable than a tertiary. So the tertiary ones have only SN1 reactions because there doesn't allow for a backside attack, whereas a primary carbocation does. So SN1 solvents would best be Protic polar solvents, so ethanol, ammonia, water. These solvents have hydroxide or NH groups, so they'll form hydrogen bonds with the carbocation intermediate. So you can see that here. And this will stabilize the carbocation, preventing those backside attacks. On the other hand, SN2 reactions occur best in aprotic polar solvents, so ethoxyethane, propanone, and NN-dimethylformamide, or DMF. These solvents don't have hydroxyl or amino attached to them, so they can't form hydrogen bonds. So that will allow the nucleophile to remain reactive and favors the SN2 mechanism. So it does allow for backside attacks. So there are a few factors that affect the rate of reaction. So one is the type of halogenoalkane. So tertiary ones are the fastest, and then secondary, and then primary. And then the type of nucleophile. So negative nucleophiles are more reactive than neutral ones. And then the leaving group. So iodine would be the best leaving group due to the weakest bond strength, and so it'll react faster.